My name is Mikael Bergqvist, as you heard. I'm the R&D manager for Orexplore. We are based off of Stockholm, or Kista, outside of Stockholm, in Sweden. We're a company that is now about 9 years old, founded in 2010. And we've been developing this technology since then and launched our first product, this GeoCore X10, in April last year as a commercial offering. And today I will be talking about how geological structures and minerals and density data from looking through the drill core can be retrieved and used in various ways. Some of this data comes from a large research project together with 14 other organizations actually in the world, but mostly from Europe, founded by the European Commission as part of the Horizon 2020 project and or program. And this is also there is also some use case from Australia. First, a little bit about our technology. We will not be having, as initially envisioned, the ability to host you for a visit at our facilities here in Bassendean. We have a branch office here, and working with the Australian companies off of this office. But I changed the presentation a little bit, and I try to introduce some more of the technical aspects. And also we have this 10-minute slot after the presentation for questions, so I welcome the questions. And also I will be here the whole day, and also my colleague Russell, so we are here for answering questions and discussing with you. So we are using a combination of X-ray tomography, X-ray fluorescence, and direct measurement of the mass. And we use minerals as the building blocks for trying to model the material in the cores. Here is how the system is constructed in a schematic way. So there is a transmission camera that actually takes images of the transmission, the X-rays that are transmitted through the core. And we have some XRF spectrometers that are looking at the radiation that are emitted from the interaction with the core. And we use a high energy X-ray source. And the importance of that is something I will come to just in a couple of minutes. First, this is a little bit of background of the X-ray fluorescence. From some of the questions last session, it's apparent that some of you are familiar with the XRF technology. And for those who are not, this is just a brief overview. So gamma photons are impinging on the material that we are looking at and trying to examine. And they will excite the atoms, whereby some of the electrons will be actually no longer in their orbits that they were having before, what we call the shells, the M, L, and K shells in this case. And these electrons that are knocked out of the atom will leave an empty space or a vacancy, and it's very rapidly filled by some other electron from some other shell, as it were. And the transitions between the outermost shells is a slightly lower energy, and the transition from the K shell to fill the K shell, if the K electron has been kicked out, especially from the heavier atoms, that will be representing a quite high energy also from the fluorescence. So here is a curve showing the actual, we call it the penetration depth, is actually the power of emission from within the core. So if you have excited some of these atoms that are inside the core with the gamma rays, there is 100 times deeper interaction depth. For instance, in the region of some of these precious elements like gold, platinum, iridium, and so on and so forth. So we are actually quite powerful X-ray beam that's being emitted from the elements itself. And that's because we are here looking at the K peaks and not the L peaks. And also in the question in the last session of overlap, by using the K peaks, where it's possible also for the heavier elements, we can avoid some of this overlap. That is it's a very crowded place amongst the lighter elements emission lines or peaks. And something that is becoming more and more evident is there is more knowledge to be found from using continuous data sets. And this goes for geological structure, mineralogy, geochemical data, particle sizes and their distributions and directions, density, rock quality designation, and core recovery. First, let's have a look at the mineral structures that we can retrieve from tomography. First of all, it's visual. Suddenly, everybody can see it, not only the structural geologists, but everybody can see it, and the structural geologists can really have a go at it. It's three-dimensional. No longer does people have to use the televiewer, making two-dimensional photographies of the inside of a hole. It becomes suddenly obvious. So here is the view that the user of the software will see when they have scanned the core. And this is just a little piece, but it's continuous data, so you can retrieve any of it and work with it. And this is 0.2 millimeter resolution of this volumetric data. And that's the standard sort of resolution. And it can be even enhanced if people are interested in more detail about smaller particles. The structures we saw in the last image can then be annotated. So the planar structures, here is, for instance, the interface between some sulfuric minerals and some other. It's an interface here with some protruding sulfuric minerals into the other matrix of the core. We have a better look if we turn it around a little bit. So by looking at these structures in 3D, and they can be made completely translucent as we saw at the previous image, it's very easy to attach a plane and adjust it to that interface. The linear structures, and we might have the same issue with the... No, it's actually working directly. So to show the linear structures, I'm using an animated sequence here from the interaction with the software. And the user selects what type of linear structure he wants to annotate or she wants to annotate. And then just lines up that structure so it's on top of itself, so to speak, and then selects and marks it in this way. And both the planar structures and the linear structures are, of course, then editable, and you can also comment and say what type of structure it is and export the data, as we'll see in the next slide. So here is the dialog showing the alpha beta angles, and there is room for commenting what type of structure this is, if it's not only the the default types of structures that we have identified that's available by the drop-down system. Here's another example of automatic annotation of particle directions and lineations. The amount of data that we see now is becoming quite huge. So, for instance, from one of the participating mines in the X-Mine project, a mine in Greece that is run by the Canadian company Eldorado Gold, they have now easily annotated over 600 planar features for about a 100-meter core. And this is something that was taking in a very short time. And it's something that takes very long time manually or completely manually, and by not having any three-dimensional representation of the core. Yeah, so yeah, it's a small glitch. Bear with me with those glitches with the projector. Anyway, taking it a step further, we can even automate it. So first, there is this easier manual annotation procedure that we saw, and now also doing it automatically. So here is a piece of core where the direction and type of direction or elongation of these particles has been automatically identified, and these so-called tadpole plots are showing the direction of the elongation for these particles. The same thing can be done for identifying lineations. So here is a drill hole with the data being selected and brought up for closer view. And we see it very clearly by ourselves, but the automatic software that identifies this picks it up very nicely. This type of data can then be, of course, these directions and these data sets can then be also plotted using stereo nets or wolf nets or whatnot. So it's been possible to either export or use within the software itself. The other type of data that we produce is, of course, the concentrations maps like this over the whole drill hole. So we have the in this case concentration of zinc, lead, and iron plotted along the drill hole. Here is the schematic view. It's zoomed out of the three-dimensional structure of the hole, of the core. And here is all the elements from sulfur up to bismuth, and what elements have been detected and to what concentration. And by hovering over with the mouse, you would see the actual concentrations in all the locations. And here is the tabular format for those elements. And these elements can be, of course, selected in arbitrary ranges and exported. So it can be done like the normal composites. It can also be shown for like the selected piece that you're looking at for doing the structural analysis. We show the density variation in the same way with the diagram, and here we can see the measured density parts and also those density variations that come from applying the knowledge of the mineral structures or the mineral composition that is underlying that piece of the core, and working out the variation that would have been there had we looked at the actual 4 millimeter intervals of mineralization instead. These solid lines, that's what's measured in the system. It's measured over the sample length of these sample tubes, and measured by actually weighing the sample and calculating the volume, so we have it easily accessible. We see a clear dip in the density here, coinciding with a quartz vein. I talked a little bit about mineral concentrations, and here is a plot in the same way over the drill hole of galena and sphalerite And for comparison, we put up the zinc and lead just to see how it coincides. We also will be releasing in the next version of the software the RQD. It's still like we have not decided exactly how it will be presented. So currently it's like in a pop-up window from the software. And we are working together with geologists to understand how is it best viewed now that it's continuously being presented over the core. This is one possible view of it. So the data and then a zoomed-in view on the side. The machine itself is about 2 meters high, slightly more than 1 meter wide and 90 centimeters deep. And it uses this combination of techniques, gives these tomographic images, also weighs the sample so that you get the density variation, and we are targeting the base metals with this machine. It measures from sulfur to bismuth, and the goal for it is to measure at the speed of 6 meters per hour. So working with the GeoCore, here is working with oriented core from the training material for that. This is the core tray, and then some rendering illustrations. Putting it down and putting it in the same way as it was when it was the orientation line was drawn. Inserting it in the sample holders and taking the sample holder and insert it in the machine. So the system was designed for sitting next to a drill rig so that the driller actually could do this procedure. But now it has been more apparent that the companies don't want to use it that way. The customers want to use it. First of all, it's a different, it's a slightly different view on what you can let the drillers do in Sweden and in Australia. So it's also it's apparent that the companies want the machine to be in the core shed or close to the core shed, because there are a lot of older cores that they want to feed through the machine as well, and not only the newly freshly drilled cores. And also it is like more centrally located, and it can be not only older but cores from another campaign maybe that can be put through that machine. So we insert up to 4 meters of cores at one time in 4 slots, and then push the button, and the machine will automatically scan the whole set of data. So here is a case study from this X-Mine project. It's a mine in central Sweden called the Lovisa mine. And here is an example how the drill core transmission data and the fluorescence data is used for doing structural and geochemical data and then well correlation, and put the data into a 3D deposit model, in this case modeling the lead zinc and the zinc ore. And then also reiterating this to see should there be some other drilling done in other places to complete the model. Some insights that we get from this. Some of you will have seen this from another presentation previously, but I like it. It's a 40-year-old experienced, in the field, being 40 years of experience. He told me that it was a little bit embarrassing now having to admit that what had been previously interpreted as dominated by brown sphalerite with brown garnet as an accessory is now believed to be the opposite. Another example from an Australian mine, Gold Road Resources or operation, shows the detailed understanding of distribution of coarse gold in relation to veining and fracturing that is associated with the mineralization. And it also discovered that in this particular deposit, most of the coarse gold was associated with fractures subparallel to the main vein contacts. And to end it off, to be able to make the structural measurements from oriented core and getting the alpha and beta angles and then go into dip and strike was a feature that they had great use of, as seen in this press release from Gold Road Resources, where they actually show the coarse gold, where it's located and how it's associated with these structures. This data is then exported into the Leapfrog software. The previous software we saw for modeling was the GoCAD software. And that concludes my presentation. I think we have time for questions.
Sorry, just a question on the core diameter.
Yeah.
I had a look at the instrument some time ago, and NQ was limited to NQ size core. Has that changed?
It's NQ2 is the biggest diameter, and it's actually so that some of the clients have started to understand that the previous sort of rules that made them choose, for instance, HQ for scanning, is due to that they have to gather more material, more of the stone itself, to be able to get statistics from the traditional sampling of the chemical elements. So, since we are measuring the whole volume, we might get even the same amount of data scanned and analyzed as if you take half of a HQ core and send it to a lab. So we have seen some of these mines in the X-Mine project. For instance, the Azurel Medet in Romania. They, for this purpose now, they changed from HQ down to NQ. And sometimes it's not possible because of the terrain and so on. But it's a geometrical limitation of the machine. And if it becomes interesting enough and people don't want to change, we have to probably start accepting bigger cores. But for now, we don't do it.
I would imagine that the change from NQ2 to HQ would increase significantly the amount of data that is produced by the machine, and would therefore result in perhaps longer processing time. Is that correct?
That's right. And I mean, the same. It is true that it would take longer time to process the data, and I also think that drilling HQ takes longer time, and the design criterion for the machine was from the beginning to keep up with the drill rig. So that's sort of the aim for doing 10 minutes per meter, and it's also true that if we sort of would like to have a better resolution, like I mentioned that the machine is intended for the base metals currently, and we are working on a more precise spectrometer that will also increase the sensitivity for low concentration precious metals. But it's still being used by lots of gold exploration companies, because they see since if they have visible gold, if they have coarse gold, and sometimes they would be interested in also finer resolution of imagery, and that also produces more data. So if you increase the resolution by like a factor of 2, then you would increase the amount of data as the cube of that, so it would be 8 times the data, and now we produce 2 gigabytes of data per meter. So it's true, both cases like that will produce more data.
The graph you showed with the penetration depth or the escape depths for the
Yes.
X-rays, showed kind of relatively limited depths for some of the lighter elements.
Yeah.
And you talked about modelling. I just
Yes.
wondered what parts of the volume are kind of modelled based on the tomography, or kind of how is that data created for the entire core volume?
So the whole core is, the whole internal part of the core is modeled from the tomography data, and it's identified being the same as what is been found on the outside. And some of these elements are so, has such a shallow penetration that they wouldn't even go through air. And it's really, it's no chance of picking them up deeper down in the core, and that's just the laws of physics. But by using this this modeling technique, when we see the same properties from other physical aspects, we can conclude that they are present still. You saw the material looks the same color, the same texture or distribution of particles will go throughout the core and be seen in the whole volume. If it's not like a very, very dense material like high rich lead or some other material which has a very high attenuation power, since I mean the machine is protected by lead on the outside, so that's impenetrable by its own nature. But it's also something that's with this technique that we are using, we are scanning the whole, even for the lighter elements, we are scanning the whole surface, so the full 360, the full surface of the whole core, and that is the sort of the minimum. And then we go deeper and deeper and cover more and more also of the volume when it comes to the heavier elements. So it's a continuum from that, but at least from the whole surface of the core. So it's as far as we know, the technique that sort of exposes the largest area of the core to analysis.
Can you handle half core?
Yeah, we can handle half core, and that's very commonly encountered because people have already cut the core. The old core is already cut, and they want to put it through this analysis as well. And also, as Mikael explained last session, all of these new techniques are faced with these old cores being in the core yard, and we have to be able to deal with it. It will introduce some actually some artifacts currently in the corners, in the sharp corners of these half cores. So that piece of the core has to be taken a little bit cautiously, but we have encountered it many times.
Okay.
But normally we would prefer to first scan it and then cut it if people want to do some comparative analysis, because it gives better results.